So now that the simulation is running, it will take some time, and we'll use the time just to continue with the lecture with the second part. So in this part we will talk about the second technique that we are going to use, and that is the non-equilibrium Green's functions technique. In order to use the non-equilibrium Green's functions technique, we have to convert our bulk configuration with the interface to a so-called device configuration. And the device configuration in VNL looks something like the following. So you have essentially three parts. You have a central region, and then you have the two electrodes, the left and the right electrode. And in the central region you typically have what you call the scattering region. In this case it would be the interface where the incoming phonons are scattered. The special thing about a device configuration is that the two electrodes can be considered somewhat semi-infinite. That means that, for example, the left electrode is bounded to the right side by the central region, but to the left side it extends infinitely by periodic repetitions or periodic images of the electrode itself, and the same for the right electrode. And in order to set up such a device configuration, in order to be a valid device configuration, you have to obey some constraints, and in particular the two outermost regions in the central region, the so-called electrode extensions. So the first, that means the first layers in the central region have to be an exact replica of the adjacent electrode. So that is something about the device configuration in general, and in this case we will use the device configuration for non-equilibrium phonon transport. So here we have a purely harmonic model of our system. That means no anharmonic effects. Everything is treated in the harmonic approximation. So the term non-equilibrium comes from the idea that you take both electrodes, and each electrode is at equilibrium with a heat path at a given temperature T left and T right, and that can be different temperatures, and that leads to different phonon occupations here called N phonon in the left and the right hand side. So the distribution of phonons in the two electrodes will be different and will depend on the temperature. And those different phonon distribution actually leads to a non-equilibrium phonon distribution in the central region. So if we want to calculate such a system, we can write, so to say, the dynamic equation of this system, which can be considered kind of the equivalent of the Hamiltonian, and this looks something like the following. So you have a matrix, and on the diagonal of the matrix we have block matrices D, which are the dynamical matrices of the uncoupled subsystem. So the dynamical matrix of the left electrode, the dynamical matrix of the central region, and the dynamical matrix of the right electrode. And the off-diagonal blocks denoted with the letter V are the coupling force constant matrices. So the coupling matrices between the left electrode and the central region, and the left and the right electrode and the central region. And we can set up this equation, which basically looks like the normal phonon equation that you would solve, but instead of solving this equation directly, which would not take into account the semi-infinite properties of the electrodes, we instead use the Green's functions technique to solve this, which is something like basically inverting this matrix. I will not go into the mathematical details of the Green's functions formalism, but once we have calculated the Green's functions of this method, we can use them to, for example, calculate the propagation of an incoming phonon mode from the left electrode through the central region to the right electrode, and that we can basically use to calculate actually what fraction of an incoming phonon mode at a certain frequency is able to be transmitted through the central region and into the right electrode, and what fraction is reflected at the interface. And by doing that we can calculate the phonon transmission spectrum, which is basically the sum of the fraction of the transmitted fraction of all phonon modes at a given frequency. And this would be an example of two phonon transmission spectra. The blue one is the phonon transmission spectrum of a perfect system, in this case a perfect carbon nanotube where no intrinsic scattering would be observed. And here you see you have integer transmission. So each phonon mode, since there is no scattering, each phonon mode would travel undisturbed and unscattered through the central region and would fully be transmitted to the right electrode. So basically the transmission of a perfect system is actually the number of incoming phonon modes at a given energy. However, if you have some scattering, some impurities, for example, here we have C14 carbon atoms, carbon isotopes as impurities in the carbon nanotube, and in the green line you see actually that the transmission is reduced compared to the perfect transmission spectrum of the carbon nanotube. And that means we can use this transmission spectrum kind of as a measurement how much phonon energy is transmitted through our system and how much is reflected. And once you know the transmission spectrum, you can actually use the so-called Landauer formula to calculate the thermal current at a given temperature difference between the left and the right electrode. So basically what you do is you calculate how many phonon modes are occupied at the temperature of the left electrode in the left electrode at a given frequency. Then you calculate what fraction of those phonon modes is transmitted to the right electrode and the energy of those that each phonon mode transports, and then from that you subtract basically the opposite contribution, that is the phonon modes coming from the right hand side transmitting through the central region and ending up in the left electrode. That is this contribution. If you take the balance of those two, you get the thermal current through the central region at a given temperature difference. And you can not only calculate the thermal current, but you can actually also calculate the conductance here in the limit of infinitely small temperature difference delta T. And basically what you do, you take a Taylor expansion of this difference and divide it by this delta T, and then you get to the following formula for the thermal conductance at an average temperature T. So once you have the transmission spectrum, you can calculate both of them in a more or less straightforward manner. Fortunately, you do not need to calculate the two expressions by hand, but we actually have a plugin in VNL that helps you calculate those quantities from the transmission spectrum. So the properties are the application limits and application limits of the non-equilibrium Green's functions technique for phonon transport are the following. NEGF phonon transport includes ballistic transport. That means the phonons travel only ballistically through the central region, and we include only elastic scattering due to disorder or boundaries in the scattering region. We fully include quantum effects, in particular quantum statistics, which means that it's applicable also at low temperatures. What we do not include, as I mentioned in the beginning, is anharmonic effects, and in particular inelastic phonon-phonon scattering. So the NEGF phonon transport technique is particularly applicable for interfacial conductance, because here typically elastic scattering at the interface provides the largest contribution to the thermal resistance of the interface. It is due to the full inclusion of quantum effects applicable at low temperatures, and you can also use small configuration. That means you do not have the finite size problems that you have in the non-equilibrium molecular dynamics technique. Large phonon wavelengths, as I showed in the previous, in one of the previous slides in the previous part, where you need to increase the cell size to include the entire phonon wavelength in any MD simulation. Such large phonon wavelengths are here taken into account implicitly via Q points. So basically in the same way as if you would calculate the phonon band structure of a unit cell. Here you also specify how many Q points you want to use, how many phonon wave vectors, and by that you can calculate the entire phonon spectrum also for large wavelength based on a small cell. So that is basically the same principle, and in the hands-on session we will show you how to do that. On the other hand, NEGF phonon transport is not applicable to calculate the bulk conductivity, because the one of the main dominating contributions to the resistance in bulk conductivity is actually inelastic phonon-phonon scattering, and that is not accounted for by this technique. And also due to the lack of anharmonic effects, we would expect some more severe deviations, especially at high temperatures. So just to summarize the two techniques, if you want to calculate bulk conductivity, you can use the non-equilibrium molecular dynamics technique. However, you need to be careful with finite size effects, and it might be necessary to extrapolate the conductivity to large systems. If you want to calculate interface conductance, you can use both NEMD and NEGF simulations. Here we have the two limitations that NEGF includes only ballistic transport, and NEMD you always need to check whether you are more or less converged with respect to the system side. And one of the nice things in the Virtual Nanolab and ATK is that it's one of the only codes where you can use both techniques and actually can compare the results and check if any of the limitations is so severe that one of the techniques gives completely different results than the other one, or if both give more or less the same results. But that was everything for the second part of the lecture, and we'll continue with the second part of the hands-on session with Casper. Thank you very much so far.